What do a beating heart, a symphony, and a rumbling earthquake have in common? They all create sound. It's a fundamental part of our lives, but what is it really? In this video, we're going to unravel the physics of sound, from the vibrating source to your brain's perception. Let's dive into the incredible world of these invisible waves. At its core, sound is a mechanical longitudinal wave. Let's break that down. Mechanical means it needs a medium to travel through, like air, water, or a solid. This is why, in the vacuum of space, no one can hear you scream. Longitudinal means the particles of the medium vibrate parallel to the direction the wave is traveling. So, how is it made? The story starts with vibration. When a guitar string plucks, a drumhead is struck, or your vocal cords move, they shake back and forth. This vibration pushes and pulls on the surrounding air particles. The push creates a high-pressure zone called a compression. The pull creates a low-pressure zone called a rarefaction. This chain reaction of squished and stretched air moves outward from the source, like a wave, carrying energy with it. The air molecules themselves don't travel all the way to your ear. They just pass the energy along by bumping into their neighbors. We can describe sound waves using three key properties, and each one directly affects what we hear. First, amplitude. This is the maximum displacement of a particle from its resting position. Think of it as the height or intensity of the wave. In terms of sound, a higher amplitude means a larger pressure variation, which our brains interpret as greater loudness. A gentle tap on a drum has low amplitude. A powerful slam has high amplitude. Second, frequency. This is the number of complete wave cycles that pass a point every second. It's measured in hertz, hertz. 1 hertz means 1 vibration per second. Frequency is the physical determinant of pitch. A high-frequency sound, like a piccolo's note, has a high pitch. A low-frequency sound, like a bass guitar, has a low pitch. The human hearing range is typically from 20 Hz to 20,000 Hz, though this shrinks as we age. Sounds above this range are ultrasound, used in medical imaging, and sounds below are infrasound, produced by things like earthquakes. Third, wavelength. This is the physical distance between two successive compressions or two successive rarefactions. It's inversely related to frequency. High-pitched sounds have short wavelengths, and low-pitched sounds have long wavelengths. You see the flash of lightning, but hear the thunder later. This is because light travels incredibly fast, but sound moves at a much slower, finite speed. In air, at room temperature, that speed is about 343 meters per second, or 767 miles per hour. But the speed of sound isn't constant. It depends on the medium. The key factors are the density and elasticity of the material. Sound travels faster in liquids than in gases, and fastest in solids. Why? Because in solids, the atoms are packed tightly together and connected by strong molecular bonds, allowing vibrations to transfer energy more efficiently. This is why you can hear an approaching train by putting your ear to the rail long before you hear it through the air. The general formula for the speed of sound in a solid is the square root of its Young's modulus divided by its density. For fluids, it's the square root of the bulk modulus divided by density. Now, let's follow a sound wave on its journey into the human body. Your ear is a remarkable transducer, converting sound energy into electrical signals for your brain. Step 1. The outer ear. The visible part of your ear, the pinna, funnels sound waves into the ear canal, directing them toward the eardrum, which vibrates in response. Step 2. The middle ear. The vibrations are transferred to 3 tiny bones, the ossicles, the malleus, incus, and stapes. These bones act as a lever system, amplifying the force of the vibrations to overcome the impedance of moving from air to fluid. Step 3. The inner ear. The stapes pushes on the oval window of the cochlea, a spiral-shaped organ filled with fluid. This motion creates a travelling wave along the basilar membrane inside the cochlea. Sitting on this membrane are tiny hair cells. These are our actual sound receptors. Different frequencies cause the peak of this travelling wave to occur at different places along the cochlea, stimulating specific hair cells. This is the place theory of hearing. Step 4. The brain. When these hair cells are bent, they send electrical signals through the auditory nerve to the brain. The brain then processes these signals, interpreting the patterns as speech, music, or noise. Sound isn't just about information. It's also about energy. The energy and power carried by a wave are crucial. The power of a wave is proportional to the square of its amplitude. So, doubling a wave's amplitude means its power increases by a factor of 4, making it sound significantly louder. This energy can be harnessed. Ultrasound, sound with frequencies too high for us to hear, is used in medical imaging to see inside the body without harmful radiation. Sonar uses sound waves to map the ocean floor and detect objects underwater. The field that studies all of this is called acoustics, a branch of physics that spans from designing concert halls to controlling noise pollution. So, let's recap. Sound is a longitudinal mechanical wave born from vibration and characterized by its amplitude, frequency, and wavelength. It travels at different speeds through different media, and its journey into our brains is a marvel of biological engineering. From the simple pluck of a string to the complex processing in our brains, the physics of sound is a beautiful interplay of energy, matter, and perception. It's an invisible force that allows us to communicate, enjoy music, and understand our environment. What phenomenon in physics should we explore next? Let me know in the comments below. If you enjoyed this deep dive, don't forget to hit that like button and subscribe for more content. Thanks for watching, and see you